All right, good afternoon, everybody. We are picking up our project on the NFL's Big Data Bowl for 2025 version. It's a Kaggle competition where you are trying to use pre-snap information to make post-snap predictions. You can do it a variety of different ways. It's pretty open-ended. So you have choice in what you want to do. Right now, we're just working on a model to predict run versus pass. And then we'll try and also go into some of the prediction, like given a certain scheme here, what would you expect the offense to do if you're looking at it defensively? Or if you're on a certain formation, what would you expect the defense to do as far as their reaction or their matchups? We are at about a 75% accuracy for run versus pass. And the surprising thing there is that we are using a very basic logistic regressions model. There's no real hyperparameter tuning. All we're doing is we're doing some very basic data manipulation in terms of keeping things as binary as we can. So one-hot encoding. So the field that has all the team names on it, now you have one-hot encoded where it's for all, there's 32 columns instead of it being one column with a yes or no for each one. But we're hoping to add a couple more fields here today to try and get better performance on predicting the play outcome correctly. And then we'll move into more of the scheme side of things. So given we're going to add more personnel, and then based on that, can we predict the scheme that the offense would be in, and then work on the defensive side of things, as well as how the defense should react to the offense or vice versa. So going through this quickly for what we've done so far, we've seen overall the data is pretty clean in terms of its presentation. The specific cases here, for example, yard line side number, the reason why there are 224 plays here in the play table is that these are on the 50-yard line, and so they are on neither side of the field in terms of offense or defense. Then similarly here, the offensive formation of receiver alignments, these are the kicking plays, and so there won't be an alignment or an offensive formation there because when they're doing that, the kick formation is different, and that's not actually qualified here. Same thing for the pass result, pass length fields. Well, these are the running plays that these are happening, and so there's nothing there. Same thing for a pass length. These are things like incompletions and those kicking plays, rushing plays, all kind of grouped together. Some of these fields here towards the end are kind of irrelevant to us because we're not looking at like how the defense is aligned yet, but these are based on the play. What was the run concept of the defense? Well, if it's pass play, you wouldn't have rush concept in there. Same thing for special teams. So then we wanted to look at the individual fields here that we were trying to get an idea as to what we were doing in our exploration. So first thing we did was look at rushing yards, just to try and get an idea of what was the average rushing play. We saw here it was 0.08, which seems really wrong. Like, why would teams even bother trying? But then I had quickly realized that this player play table has all of the players on a field for a given play, and there are 22 players on the field. So only one will have a rushing yard, which already means that you would reduce this significantly. And then there's no filtering here, so it's all the plays possible, right? So those kicking plays, those passing plays are also then showing in here and dramatically reducing the average down. So then once we figured out that there is a had rush attempt flag field in the data, we're now seeing that the average rush attempt resulted in about 4.5 yards. Similarly, for receptions, we see that there's a pass reception field here, and that brings the average from 0.17 up to 10.9 yards per pass reception. One thing to keep in mind, and this will come up again when we talk about our model, is that these are the actual pass receptions where it was actually completed to the receiver. So incompletions are not in this set here. Then we tried to see, just do some basic high-level analysis, grouping by the teams for these. So on a rushing attempt, group by the teams, what was the average, and then sort top to bottom, basically, or the largest to the smallest. So here we saw Chicago, Las Vegas, Seattle, Jacksonville, Baltimore, all the highest rush offenses. And then the flip side, the least were Tampa, LA, Indy, Cincinnati. And we did the same thing for pass receptions here. And then we started to work to group our data together, so that way we could get an idea of how teams are performing on plays, and then also do that for individual players. And what we realized here is that in the data set, there's only the ID of the player. There's no information about that. That's actually off in a different table. And so we worked to pull that information in here, and then you can see, who was the best or highest rushing average was actually Taysom Hill. And the surprising thing here is that the highest players tend to have fewer rush attempts. They would think there's only like 1 or 2 a game if you want to think of a 16 or 17 game season. How many of those have? But when they do, they're pretty effective. And had we not put in this filter for them having to have greater than 10 rushing yards, you would see those single big effective plays appearing here. So I believe without this, like the top one was there was a player who had 1 rush for like 70 yards. And so their average rushing yard was like 70 yards, but they only had a single attempt. And so that's something to keep in mind when you're looking at more predictive data, if you don't want these single individual outliers to have an impact on your model. And so you need to do some filtering here for those. We had started to add in more flag fields. This one was to try and see if there was any motion on the play to see if that gave us better predictive outcome. And when we had actually done the comparison on the model, that had actually helped to increase by 1.5 percentage points flat with all the other things that we had already had in the information here. These queries here are basically just grouping the data together, so that way we can join them all to a singular data set, so that way we can do the comparison. This is a little bit more of the data analysis, where we're looking at, now that we have the different formations in there, what are the receiving yards in terms of the average versus the number of times that it happened. And then trying to do this also for individual teams. And since we'd seen that Tampa Bay was the lowest rushing average per play, can we look at their things and see some stuff that quickly jumps out? And what I noticed here, and I'll get to the individual plays, is that it became very predictable for when they would actually attempt a rush during the season. So what we were seeing here is that most of their rushing attempts were actually from the single back formation. Very little would come out of the others. There are a few games here where it is a little more balanced, but still for the most part, if they're in the single back formation, they're almost never likely to throw the ball. So if you see a single back come out, just line up, stop the run. Sure, you may give up a few extra yards in the pass, but for the most part, you're going to be way more effective in it. And you can see some of these games are extremely imbalanced. You're talking 15-2, 16-1. A few games where it was like they barely attempted rushes, but then the flip side became true. They became heavy on the shotgun formation in terms of passing. Here's another one, 12 versus 2, 12 versus 1, where Tampa's offense became, I would say, very predictable in terms of as soon as you saw the alignment of the offense, you were likely going to know what they were going to do in terms of the pass versus rush on a given play. So then worked here to create a very basic model, a little bit more of the data manipulation after we'd done the initial prediction. We came back and we created buckets for certain fields to add to there. So this one here, we needed our flag to know whether it was a rush versus a pass play. And so if there were rushing yards on a play, well, then it's a rush play. If not, then it's a pass play. And we started out with these very basic categorical variables to group them in. What was the formation of the offense? What team was it? And how were their receivers aligned? And with just that basic model information, we had gotten a 70% accuracy in terms of the model. So 3 fields, you with 70% likelihood would know what was going to happen on a given play. And then we worked to add some more fields into this model. So we added the quarter that the game is in, what down it is. Yards to go, we actually made into a bucket. A score differential, which is the combination of the home score minus the visitor score. And then the absolute yard line is how far the team has to go from where they are in the field to actually get to the end zone. So not just how many yards to gain, but how long to go for a touchdown. And so this logic here helps to calculate the score differential. So if your team is the home team, then you're going to do home minus visitor. Seems pretty straightforward. And then the opposite. If you're not the home team, well, then you're the visitor, and you want to subtract your score, or you want to subtract the home score from your score to get the differential. And the idea here is that teams will play differently in different game situations. So if you're behind by 1 touchdown versus 2, you're going to handle the game a little bit differently, especially as the game gets closer to completion. You will have less opportunities to run the ball because that will keep the clock running. And then going here, this was the bucketing I was talking about. So yards to go, sometimes you'll see this during broadcasts of the game. You have these, what they'll call short yardage situations. You have 3 or less yards to get a first down. You then have a medium yardage situation. It's basically 4, 5, 6, and 7 yards, and then long. So first down will always be a long situation, but depending on how effective you are on first down, will change the bucket here. The absolute yard line number here, I just made some basic cutoffs. So when you're 20 yards from scoring, this is called the red zone. So I'm defining that as short here in terms of what to expect on the field. Then after about 50 yards, you're not going to even attempt a kick. So I listed that as long. And then everything between was the middle of the field. I had worked on some logic here to create the amount of time remaining in the game. We do have the clock, but we don't have a full game comparison. So if we're in the first quarter, we're going to take the game clock and we're going to add 45 minutes to it, right? Because you still 3 15-minute quarters remaining. Then same thing for the second quarter, except it's going to be 30. And then actually the third quarter here, I just noticed this typo. This should be 15. So I'll make sure to update and fix that. And then this is the game. So there is this is the final 2-minute warning. This is the last 2 minutes left in the game. And then there's game timer. This is about 3,200 to this. So this is the 2-minute warning before the half begins. And then looking here, you can see across the game, there's about 1,200 plays that happen in those final 2 minutes of each half versus the whole other time, there's about 11,000 plays. So then using these new fields here, we created a secondary model. This one, it actually got up to 74%. And then instead of using the buckets here in terms of the yards to go as well as the full field position, we treated these as numbers instead of using the categories. And that actually gave us even more value here, where we got up to 75% accuracy. Then just to make sure we're not just kind of blindly going down the path of logistic regression, we made models for random forests as well as support vector machines. And here we see random forest is still trailing behind the logistic model. Before we added those new fields for yards to go and absolute yard line number, it was actually more dramatic. So the base model had 70% accuracy, but then the random forests had about 68% accuracy, or sorry, 65% accuracy, and the support vector machines had about 68%. So the reason why you would, if you could use the models, you would actually try and stay with the logistic model, not just because it's the best performant, but because it's the easiest one you can use to explain to non-technical people exactly what's happening. Random forests is more black box. It's just going to keep splitting the data until it gets the best prediction. but you can't always tell easily how it got to that conclusion, right? It's literally, it gets its name random forest because you have groups of decision trees randomly being selected to try and get you the outcome. And then support vector machines, it's easier than the random forest in terms of getting a response back, but it's still challenging and not as straightforward. So given the audience of this, where we're going to be presenting our findings to an NFL audience, that they are not, I would say, as technical on the data science or machine learning side of things, that it would be better to go through and train or use this logistic regression, because you can use the coefficients to say how important is each of these pieces of information. And so when you're looking here, we saw from the base model, just these 3 fields gave us 70% accuracy. And now we've more than doubled the amount of fields to get a small increase in the model. I say small relatively because you're going from 70 to 75%. But we would have to do more, and you can see how quickly we can get a pretty good model really easily. But now we have to continue adding more and more information. And as we add more, it's going to be harder with a model like random forest to actually explain what's happening. Whereas with the logistic regressions, we will always have the coefficients. So that way we can say, oh, this is the most important in a given situation, or these are the most important fields for us to know. So with that, today we're going to look at changing our data slightly to get an idea of who the players are on the field for a given play, to see if that will have more predictive power as well. I would imagine for a team like Tampa Bay, since they had the single back formation was their most popular or most likely to run the ball, that there were probably 1 or 2 players that if they were on the field, it was way more likely to be a rushing attempt versus not. And we want to prove that out with the data. So we're going to have to go back to our initial build of the data set and just try and see if we are able to generate who the player is on a field on a given play. So let's go back up here. Let me just chat real quick, see if there are questions. Oh, and I should set out the link to Kaggle so you guys know exactly what I'm referring to when I talk about the fields that we have available to us. This here is a link to a list of all the fields that are in the data, what exactly those fields are meaning or holding inside of their data. And then the type of information that you could expect there. So is it text? Is it numbers? Things like that. Okay, I don't see anything here in the chat as far as questions go. I'll check on this a few times as we go. Freezing right now. All right, there we go. Oh. Hi, Matt. You've got a question. Do I use data of the current season? So because that's not publicly available, we cannot use it for the Kaggle competition. We could if we had it and it was accessible to everybody use it, one of the requirements here is that you have to use the data provided, or it must be publicly available and free. So they provided the information from the 2022 season for the purpose of this. But if you had it for your own project and not for the big data bowl, you could use it. There are places to get that. I believe Pro Football Focus, which provides some of the data here, does have the most recent data. Who else was there? There's like a stat tracker data source as well that has the individual player locations on a given play, but that's not accessible to us because those are paid services. And so for the purpose of the big data bowl, we couldn't use those. But if you had access to them and you just wanted to build your own predictive model, sure, you could use that. It would be the same thing. So you would just change, this set of queries here is how I'm grouping together the data to get the data set that I'm using. You would just make changes to that based on what you had there. Does that make sense? I'll keep an eye out for your response. All right. Perfect. All right. So the idea here for what we're working on is to try and get who are the 11 players that are on the field for the offense. So who are your linemen, your quarterback, receivers, running backs, things like that. So let's see. If I wanted to take this, let's do it this way. So for in player play, I need game ID, play ID. Right, and then grouping the data. That's this for given play. Here. Then I need to create a table. So we have oops. So we're going to create an empty list, and then we're going to go through. Oh, I'm doing this backwards. This should go up here. So we're going to make an open list, and then for given play, we want to go through and we want to basically append the players on that given play. Let's see here. Got I need to filter that first. Go here. Otherwise, I won't be able to pull out their NFL IDs and stuff. So then so player play has the ID. Don't know if this will matter, but let's just keep it there. So when you're grouping this way, it'll make sure that we have the player ID. Sorry, the player ID. This should be NFL ID. And then if it's not the best way to do this. There should be a dictionary, I think. Keep this up. Okay. So on a given play, if given play so seconds. Given play ready and Trying to decide the best way that this should be done. Because I'm hoping it treats them as strings. I'm just worried that it's going to treat them as numerics. Let me go back to the data. Play, numeric. So I need to make sure I treat each of these as strings. Let's see. I'm going to read your question out here. I quickly looked at the data on Kaggle. There are really a lot of variables, and I'm often a little lost in choosing the right ones. I'm already doing a logical sorting in my opinion, but I'm afraid I'm missing something. What do you do, a heat map or something quick? Sorry, I'm French and English is not the best. So if you have a lot of variables, what you'll want to look into is the correlation matrix between the variables. So that way you can see which of them are highly correlated with one another. It means that if you had one, the other, it gives you a lot of information about something else. So that way you can start to reduce the number of variables you would actually need in your data set in terms of actually building out your model. So this way you can quickly decide like what is useful and what's not useful. So depending on how you're doing this, I believe it's in pandas. Yeah, you can do a correlation matrix and you can do a heat map too. So let me here. So you see here, just DF is whatever your data frame is for what you're looking. This will give you your correlation matrix on what there is. So let's use this here. We're going to look at play. It's going to take a while because it's a large thing here. Could not string to float. All right, because they're all going to have to be numbers. So it's the correlation only between two numeric variables. Let me see. Here. So let's go to the data set that I'm actually got here at the end. This is the yard data enhanced. Now I've pared down a lot of the fields here, but you would need to take each of these and make them one-hot encoded. So you would see like a 0, 1 in terms of the correlation matrix to have an idea on the correlation between those fields. So like Tampa and Singleback and Rush would all be highly correlated with one another based on what you'd see. So let me try and put this together for you real quick. It's one-hot encoder. Now it's going to come out of sklearning, or sklearn, which I already have here because I'm using it in the models. And so This is the one-hot encoder. And I call this yard. We've got this. Oh. One-hot encoder. And then yard data. Okay. This is the proper way to set this up. You're then going to so we're going to do fit, and then we do the transform. I think I can do this in the same step. Is it fit underscore? Yes. Do the fit transform. And then leave that. Correlation. Okay, gotcha. Yeah. So once you have this, then you can just get your correlation matrix out, and you'd have an idea of which categorical variables you would want to keep and which you would want to drop. Yeah, if you're coming to this for the first time too, there are a lot of fields in the player play data that aren't necessarily useful to what you're learning. And then keeping in mind that our goal here is to predict, based on what we know before the ball is snapped, what the outcome would be. So for me, I'm trying to look at, if you were from the perspective of like a coach, these are things you can see on the field at a given point in time, so you have an idea of what you should tell your offense or defense what they want to do. So that's why I'm keeping it to things like, who are the players on the field, right? What formation are they in? What is like the receiver grouping look like? And what is the game situation in terms of yards, down, distance, all of that. Now, what I was working on here was just making sure we can get who the individual players are on a play, because I had not pulled that information in yet, just to try and see if it would help us with more predictive power. So on a given play, who are the 11 players that are on the field for the offense? And so that's what I was looking to put together here. So I was making a dictionary. The key was going to be the game ID with the individual play ID appended right after it. And then taking the same thing here. And then appending it on. So let's see. Interesting. Close these out. So for a given play and play ID, I guess how does this data look? Let's start here. So player play has game ID and play ID. Oh, I forgot I needed to handle this as a group. Why did that come back with no information? Why is that coming back with nothing? Let's see. I've got the game ID and the play ID. Those should be here. I do this. Okay, so these are the counts of players on the play. Those are fine. Look, each one should have 22. But then these are indexes. And these are not columns. So this would not work. Let's do this instead. I'm going to call this play. Goodbye, but don't do the count. And then players on play. This for game ID, play ID, and then teams in play group. This should then be team should I call this teams group equals teams dot group by, and this is going to be that team abbreviation. And then for team group in teams group. Player ID equals, and now this should be a team group. NFL ID. I don't want each individual one. Now that I have that, I want to go players on play dot append. But inserting, got the game ID I need to use game ID. And I need to get at play ID. Team creation. Now I've got players. And this should be let's just make this plural so we know that's all the player IDs. And then now this is players on play frame pd.data frame players on play. Team teams team players on play frame. I don't particularly like that there's some nested for loops going on here, so it's going to take a little bit to run, but that should get out what we want from the data set here, where ideally we are now getting this group of all the individual plays, and then we can work on separating those out. We're running, how are we doing? Yeah, using up a lot of CPU. So it's running, just slow. There's some limited resources here going on because I have the training running for the Pokemon model. So hopefully we can get more output there. There we go. So it took 2 minutes, which isn't too bad. And then we now have the individual game ID, the play ID, the team, and then the players that are on the field for that play. And you'll see here for each play, we have both teams, the offense and the defensive team. And we can work on joining this in now. So we have a list of the players that are on a field. Just show this. Columns. What is it? Columns of data frame. Yeah, why did I come back with index there? It should be just... Oh, because I did it as a function. And it does not need to be one. Sorry, question. Only thing I don't understand. Well, I appreciate the good comment. The only thing you don't understand is why I don't have more views. I think it's just it's a relatively new channel. I've only been doing this for about 2 months now. Twitch, I get decent amount of people who will pop in from time to time and watch. I do also do this on YouTube, which I get a few people, a few at a time. But if you have any friends that you want to tell about this, that would be useful information or share out, please do, because the more people that find this useful, the better it is for everybody. Yeah, and then if you have any recommendations on things I can do to help grow it out, by all means. I'm a data scientist. I'm not a marketer, so any good ways to get the word out there would be appreciated. So this is the yard data enhanced. We're going to do another merge here, but I'm going to change this one again. So we have yard. We're going to call this yard data motion, and then we're we have to change everything further down in the models section to do that. Otherwise, we have to go and we have to change like 40 or 50 different lines. So as we want the last data set that we have here to always be this yard data enhance. So changing the data set of the one before the merge is always the easiest. And then we just have to set that up in the join. So yard data motion here to be this new players on play frame. I should bring this down here. Let this run. We want the players on play frame here. How because we're trying to merge in new data, for now I want to do a left join just to make sure it fills in as much information as possible. And then the on here is going to be, we had the game ID, and then the play ID, the team abbreviation, should be team ABR. And then let's check out how this had done the join just to make sure. Yep, and then we have the players here. So perfect. We can now drop out this one that we don't need. To drop this. I'll take this up one and then drop the cell that we don't need. So now Yard Data Enhanced includes the players on a play. And let's see how the models handle including that. So going back here, we always need to refix the index here on the data set. Go through. This is the basic model. Doesn't have any effect on what we've done here so far. So I'll go through that, recalculate these because we reconstructed the data set. We need to recalculate all these. I don't need to see, well, it's all useful one factor. And then this was the most recent categorical, and then just do this so it's easier to read. I want to make sure that we're including, what was that in that field of players? I know it's going to be a little disjointing. I'm going to jump up here. Players, yeah. Okay. So it's there. We want to make sure players is in the categoricals, and we need to also put it here in the full variables. Let's see how the one-hot encoding handles it. Got an array because we have a list inside of that. Okay, so I need to take the players and separate them now into individual ones instead of having that list, because the list is what's throwing it to the loop. And that's why you're getting an array at the end. So let's go back here. So for players on a play, this you can do it with the F string. Because it should be player I plus 1, the thing, and then we know there's 11 players on a play, and I think it closes like that. Now it's going to take, last time it took 2 minutes, it's probably going to take a little bit longer. So I'll have some time for questions while this runs. The idea here is that once we do the merge here, instead of this being another list inside of a column, it's going to now be players 1 through 11 on a given play. And they will be in random order. I don't think it's going to particularly matter, because we'll have to encode who those players are on a given play. We'll have it here, index 10. Did I do that right? Index 10 is out of bounds. Let's take this. Let's do this in pieces. Take these out for now. And then player 10, or sorry, index 10 is out of bounds for access 0 with size 10. So there's a play where there's not enough players on the field. That's what I'm guessing is happening here. So then if the player ID do this to make sure that we have all 11, and then we need to indent everything over. And see if that fixes it. The stream's going to stutter while this runs. But now's a good time as any. If you have any questions to ask, please do. So that way, we have more to discuss while this runs. So. I'm hoping this works out, that once this runs, we can just drop it in the data frame and merge those in. Another thing to check is, will this actually work? Seems like it's finished. Yeah, that was faster this time. Let's see, merge those in. Or maybe this is just why it's taking a little bit longer. Let's take a quick look at what the data set looks like, just to ensure we've got good. So player 1, 2, 3, 4, 5, 6, 7, 9, 10, and 11. Great. So got that. Let me check here. Need to find out all the locations for the fields that we created. So scroll back through here. This doesn't change. I need to rerun the indexing. Fix. Perfect. Recreate the rush field. Score differential. Those buckets. So there we go. This just ran. Okay. Players. Now I need to change this to be player 1. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And let's see, does it handle it? Unknown categories in column 9. What's this? Predict. Unknown categories. Let's see, X. It's column 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. That doesn't make sense. Column 9 is not even related. During the transform. So it was able to fit the model, but then when it became time to do the prediction is when it threw errors. So X test. And let's take a look. Right. 2, 4, 6, 8, 9. So it has something to do with the motion since line set. Find it here in the data. to play motion value counts. It's based on indexes. So if I go to play yard data enhanced, and then once was that motion. So maybe that's what happened to throw it off, which means unfortunately we need to rebuild this query again. And because of that, we almost have this chain of things that run over and over again. And hopefully, when we get back here, we'll get good results. I have to go. Thanks for the answers, and maybe see you next time. Like your stream. Well, thanks for all the good feedback. I hope you have a great day, and I hope you find this useful. We're waiting for it to run again. It's probably going to take another moment or two. So if anybody else has any questions in the chat, please feel free to add them and drink some water. But once we get this in, the idea here is that we can hopefully start using the players on a given play to get better results from our model. That's the hope, at least. Or maybe it doesn't matter as much in terms of predictive power, knowing who the players are. But I would see certain situations where I think that would be helpful. Actually, we already see that a bit in the data. When we see the wildcat formation, where was that? Up here. Where is it? Here. When we see the wildcat formation, you get a below average outcome. And that's just because, you no longer have a quarterback in the running back, or you no longer have a quarterback in the quarterback position. You now have a running back there. And so defenses are less likely to be afraid of throws, especially big ones. So they're going to come up here and they're going to key in on rushing. And you can see here too, right? You see across the whole season, there were 10 times where there was a passing play against the rush one. And even then, the pass play had a below average outcome. Remember, the average was about 10.9 per completion. And it's not very effective. And the same thing here, the jumbo formation, usually there's an extra running back or extra lineman or fullback, if teams still use them, which is rare these days, where you're not likely to really be giving up a big pass play of any type. And you can see here, it only happened a few times where they threw it, where the majority of times they ran it. But again, defense is keyed in on that formation, and then we're basically guarding against the run. So we do see that there is an impact. The question is just going to be how much, how valuable that is to the model when it goes through. You see here, it looks like it got it, and then unknown categories. Let's see. Go up here. It was only during the predict, so using X test. It says there's a column that has just use this Google the error because I'm not sure why we're getting what we're getting here. So handle no. I'm just going to ignore. There we go. And we see we got slight predictive increase, very slight, but still an increase. So that was with the bucket fields. Let's see how we're getting it with there. So you're talking 74, still 75%. So if I'm looking at this, I'm hoping maybe we get something out of other models in terms of predictive power. That doesn't seem too likely. What we saw here is, as far as logistic regression is concerned, knowing which players on the field did not particularly make an outcome change versus information that we already knew from the formation, the game situation, things like that. So a little bit surprising in terms of what we were expecting there. I would have expected there to be a bigger impact of knowing who's on the field. But I guess just knowing that they are in Wildcat versus Jumbo or something like that, that you have a good idea of what the specific play is going to be. And you can see here, random forests, it's approaching much closer to what we have here in the logistic model. It's still less than a percentage point behind, but kind of surprising that even for them, it didn't add much. It did add time in terms of the time it took to actually run through the models, because you have way more fields that are happening with the one-hot encoding. So you made your data set much more large or much more sparse, because you'll, how many players are active in the NFL across the season? You're talking a few thousand. So your data set went from fairly tight to now it's big, large, much larger data set with a lot of zeros and ones in there, instead of it being more tight. And that's why you're seeing these times start to grow adding this. So we, if you build this out over a more long-term model, this is going to be more in terms of the cost, because you're going to need more compute resources. And then you're not really adding any predictive power with what we do here, but this is part of the experimentation phase in data science, right? Where we're trying to get an idea of what fields would be impactful are they actually going to add much beyond what we already have here? So to kind of put a wrap up on things today, like we'd spent the better part of the last hour and a half trying to work through and add receiving data, or not receiving data, sorry, the individual players on a given play to predict pass versus rush. And it didn't make nearly the same impact as other changes have made. We got a slight increase, but not particularly powerful in terms of what we were looking for in terms of the overall model accuracy. So for next time, what we'll do is we'll work on changing the data set to not just be passing completions, but passing attempts. So you have a better idea of what were the passing plays that did not work. And can we, once we incorporate those, can we properly predict pass versus rush? For those, the change in accuracy won't matter too much because we're changing the underlying target of our data set, right? We should have more plays now that are pass versus before. So we kind of need to readjust our basis. But right now, all the models are predicting around that 74, 75% accuracy. So we can make a change like this. It shouldn't be too disruptive. So what we're doing, and we would see if that causes a shift between the different model types here. So we'll pick this up on Friday for those changes. We'll come back. Like I said, we'll figure out what are the pass plays that are not just the completions, just the general pass attempts, and see if that causes any shift in our data set. For now, we will leave the player fields here. Actually, let me see, because I wonder. Yeah, so the other ones didn't change. So I actually made a mistake here. We'll wait a moment or two for these to run. So this is the other logistic regression. Where are the fields? Okay, so it's going to run off these fields. That's why. Okay, that explains then why we didn't get the unknown value error here, and we should include that here. Yep. Oh. Not random forest. What this one? And then here, and we're going to go update this as well. So like I said, this may take a few moments longer, so I'll just kind of wrap things up here. We'll see if it causes a shift, but it's really unlikely. So adding in the player data today was not particularly impactful in terms of predictive power for the models. And then for next time, which will be on Friday, going through the data and trying to change it from just passing completions to passing attempts to get a better idea on not just the plays where there were completion, but the pass. And then as far as the models go, we're not going to actually change anything in the models. We're going to kind of readjust to that new baseline of when we have the full set of rushing attempts and passing attempts versus right now we have rushing attempts and passing completions. So that's our goal for next time. It shouldn't take as long as today because we were kind of restructuring our whole data set to include the 11 players on the field. That one should be, we'll have to go back kind of to the beginning on how we originally filter our data sets to be on just the, rushing, or sorry, had passing completion to now be the passing attempt version. So we're still here waiting for the random forests. Like I said, now that we've changed the structure of our data set, you can see here it's taking much longer. Before this was about 35 to 40 seconds, but because now our data set has gotten much longer, it's going to take longer for these. So we almost doubled our time We did get now random forest has overtaken the logistic model, only slightly. We're talking 75.4%. And we're going to probably have a similar effect here on the support vector classifier, or at least I would hope it would, that we have a slightly better predictive power, but not as much as we'd expected in the logistic model. Looking at random forest, that added a whole percentage point to its accuracy. And we'll see here what SVC is. We'll give it the next moment or two to run, and then we'll wrap up the stream. If you have any other questions that you want me to answer before we wrap up, please feel free to drop them in the chat, and we'll get back to them as we wait for this to run. Probably another moment or two for that to come out. We just passed the 1 minute mark on the support vector classifier. And all in all, this was good progress for today. I was worried that we wouldn't be able to complete even getting the player information here, but we've got it now where it will have all 11 players on the field in our data set. And then there we go. So actually the SVC went down slightly knowing the players. So again, random forest's got the biggest gain of about a whole percentage point. Logistic model, not really any change in terms of the outcome here. And then the support vector, this was at 74, and then some small percentage. Now we've gone down to basically 74, so a slight decrease in terms of the power here, but kind of surprising that we had done a bunch of work to try and get the player information, and realistically, it's not that valuable in terms of what you know compared to just knowing the formation and in the game information. So that's all for today. If you see this video, please feel free to leave any comments there for things you want to look into as we continue through this. And then, like I said, for next time, we'll be working on changing it from just the pass completions to all the overall pass attempts in a game, and then rerunning these models to see if there's been any shifts as we kind of adjust to that new baseline. So for those of you who were here today, thank you for all your comments and questions. And then if you're watching this on the YouTube VOD afterwards, please feel free to leave a comment on something that you find interesting or want to see us work on as we continue through here, and I'll get to it in the next session. So thank you, and y'all have a great day.